more concept to go over regarding functions abstractly, and that is the image and pre-image of a function. The reason we're doing this is to get some practice with manipulating them. Functions seem like a very easy topic that we've understood since high school, but when we first try to understand why, for instance, a subset of A does not equal the pre-image of the image of that subset in all instances, we realize that we don't have any idea why that would even be true, let alone how to prove it. So by the end of this video, we'll be old hat at manipulating these objects and have a very thorough understanding of how injectivity and surjectivity of a function interact with the image and pre-image of subsets of the domain and the range of a function. Okay, so the definition. Let f be a function from A to B. If A sub 0 is a subset of A, we denote by f of A0 the set of all images of points of A0 under the function f. This set is called the image of A0 under f. Formally, f of A0 equals the set of all B such that B equals f of A for at least one A in the subset A sub 0. On the other hand, if B0 is a subset of B, we denote by f minus 1 of B0 the set of all elements of A whose images under f lie in B0. It is called the preimage of B0 under f. And formally, f minus 1 of B0 equals the set of all A such that f of A is an element of B0. Okay, so first thing, notice that we have to be careful regarding the notation of f, because f of A with A an element of the domain A refers to the function f, with f of A referring to the specific element of B that A is mapped to, so that f of A equals B with B an element of the range B. But if instead of an element of the set A, we put a set inside the parentheses, that is, a subset of A, then the meaning is different. If A sub 0 is a subset of A, then f of A0 refers to a set, not an individual element. So f of A0 is a subset of B. This is different from f of A. So f of A is an element of B, and f of A sub 0 is a subset of B. Now, similarly, f to the minus 1 has two meanings. First, remember that the function f minus 1, which we were talking about last time, only, in other words, the inverse of f, only exists if f is bijective. So f minus 1 has no meaning if f is not bijective. Or, as we've talked about before, the domain and the range need to be restricted so that it can be bijective. So remember, like the inverse of a sine function, you just have to cut it off. So it looks like that, okay? But if B sub 0 is a subset of B, then f to the minus 1 of B0 has a meaning even if the function f to the minus 1 does not exist. F to the minus 1 of B0 means the set of all the elements in A whose images under f lie in B0. So the important thing to remember is that if the object inside the parentheses is a set, then the object in question is also a set. So this is a set and this is a set. If the object inside the parentheses is an element of a set, then f or f minus 1 is a function. Because of this, it's entirely possible and entirely valid for this set to be empty if the elements of B0 are outside the image set of f. And also, f to the minus 1 of B0 is a perfectly valid object even if f is not bijective. So even if the function f to the minus 1 does not exist, this object still exists. And this object might even be empty. But if the inverse function f minus 1 exists, meaning that f is bijective, then f to the minus 1 of b sub 0 actually has two meanings. So this is where it can get very convoluted. because it can be taken as the preimage of B0, or it could be taken as the image, the way we defined it here, of the function f to the minus 1. But if f is bijective, then f to the minus 1 as a function exists, and so the two meanings give us the same subset of A, so there is no ambiguity. Okay? So some care is obviously needed if we're going to use the f and f minus 1 notation correctly. So some more confusion here, some things that are not obvious at first blush. As I said at the beginning, it is not in general true that the preimage of the image of A0 equals A0. It can be true, but it's not necessarily true. And it's also not necessarily true that the image of the preimage of B0 equals B0. It can be true, but it doesn't have to be. So it's easy, when you're looking at these, it's easy to just imagine, it's like, oh yeah, you take function, you take the function, you take the inverse, you're gonna go back to where you started. Take the inverse, take the function, go backwards, you're gonna be where you started. That is not necessarily true. So that point is what we're sort of going to be looking at with this video. So let's look at a function, and then it will all be clear why this isn't necessarily true. So if we have a function from the reals to the reals, so this function is a parabola, and it's offset a little bit off of the x-axis, and it's a little bit narrower than a normal parabola. So let's just look at a couple of subsets and see what happens. So square brackets AB means all the x's in between A and B, right? So if we look at from 0 to 1 here, so let A0 equal that, then so the image from 0 to 1, oh, I drew this wrong. This is actually 1, 5. So this is from 1 and this is 1. This is minus 1. Right? Because 1 times 3 plus 2. Minus 1, 3 plus 2. Okay. So that's 1, 5. That's minus 1, 5. Okay. So the image set of 0 to 1 is everything that f gives us when we put in a number between 0 and 1. So it's everything from 2 to 5. So we have f minus 1, right? So here we did 0, we start at 2, and we go up to 5. So it's this is the image set of 0 to 1. But if we take the preimage of 2 to 5, we end up with a bigger number because there's more numbers in A than just 0 to 1 that will give us 2 to 5 in the range, because 0 to minus 1 will as well. So the preimage of the set 2 to 5 is actually from minus 1 to 1, okay? When we took the preimage of the image of 0 to 1, we actually ended up with a set bigger than what we started with. And now what if we do it the other way? What if we have B0 equals 0 to 5? So if we take the image of the preimage of 0 to 5, so we're starting with 0 to 5, and then we're taking the preimage of that. So everything in A that will give us a number between 0 and 5 is again from minus 1 to 1, right? It's everything below here. So that means that it's f of minus 1 to 1. But if we take the image of minus 1 to 1, we end up only with elements from 2 to 5. So again, in this case, we started with 0 to 5 and we ended up with 2 to 5. So when we took the image of the preimage of a set, in this case we ended up with a set smaller than the one we started with. And when we took the preimage of the image of a set, we ended up with one bigger. It doesn't always have to be true, but this shows that it can be true, and this is what we're going to be exploring more. So the actual rules, then, if we have a function from A to B, and A sub 0 is a subset of A, and B sub 0 is a subset of B, then we have that A sub 0 is a subset of the preimage of the image of A0, and the image of the preimage of B0 is a subset of B0. There are times when these are equality. The first one is an equality if F is injective, and the second one is an equality, can you guess, when it is surjective. So this is what we're going to prove. And let me just remind you one more time. Remember that F minus 1 is not the inverse of F. In fact, we're looking at a situation right now where the function F minus 1 doesn't exist at all because F is not bijective. We're not going to be able to talk about F minus 1 of an element of B0 because F minus 1 isn't a function. We're only talking about sets here, okay? And F minus 1 of B sub 0 means the preimage of B0 under F, the set of elements in A that F sends into B0. Okay. So how are we going to do this? Whenever you want to prove something, start with the definitions. Don't try to be clever, just lay out what you know and go from there. In this case, we need to show that A sub 0 is a subset of the preimage of the image of A0. So to show that one set is a subset of another set, you take an arbitrary element of the smaller set and then prove that it's in the bigger set. So remember again that all of these are sets. A0 is a subset of A. The preimage of F of A0 is a set in A. The image of A0 is a set in B, and so on. Okay, so we start with A, an element of A0. So we already have that by the definition of the image of the subset A0, this should be A0, F of A0 is an element of the image of the subset A0. Now, the definition of this is the set of all A such that F of A is an element of the image of A0. And we just said that F of A0 is, in fact, in the image of A0. And so that means that A0 is an element of this set. And so that's all we needed to show. We showed that starting with an element of A0, that element is also in the preimage of the image of A0. So therefore, A0 is a subset of the preimage of the image of A0. So the point here is that this set, the preimage of the image of A0, might be bigger than A0. There may be more elements in A that go to the image of A0 than just the elements of A0. So that isn't at all obvious when you first look at it, at least to me. If you start with a set and then you do a function and undo the function, how do you end up with something bigger? But somehow doing these two operations, we lose information in an unexpected way. The reason is that there may be multiple elements in the domain sent to one value of B. And so we saw that in the example, that if this is A0, then there's actually more than just that will send it to B, right? If you think of an extreme example, if we have a function that f equals 1, no matter what your A0 is, all of A is going to send it into B, right? Okay, so the second claim is that if f is injective, then this is actually an equality. So if f is injective, then it behaves the way we would expect it to. So to prove, how are we going to prove this? To prove a set equality, you have to prove inclusion in both directions. So we've already shown that A0 is a subset of this, so what we need to do now is show that the preimage of the image is a subset of A0. We're saying now that this is true if f is injective. So we're going to have to take an element of this and then prove that it's also an element of A0, and we're going to have to use the fact that f is injective in order to do that. So injective means that if f of A0 equals f of A1, that means that A0 has to equal A1. Before we prove this, if we just look for a second at what we just said, then this is kind of obviously true, because the way that the preimage of the image can be bigger than A0 is if the function doubles back on itself. And injective means that it's not going to double back on itself. So if it doesn't double back on itself, then there's no opportunity for the preimage of the image to be bigger than this, so they're going to be equal, okay? Oh, so let's call this element f1. So we'll take an arbitrary element of the preimage of the image of A0, and we'll prove that A1 is an element of A0, okay? Just to remind us, let me just write down what the definitions of image and preimage again. It will help us just to picture what we're doing. Whoops. My stupid phone ran out of memory, so I finished the proof without filming it. So I'm not gonna write all this again. I'm just gonna start from here and point, okay? And then we'll start over. Then we'll start doing it live again.
Do it live! I'll write it and we'll do it live!
So the issue here is that there could be an element that's in the preimage of the image of A0 that's not in A0. So we have to take an arbitrary element of the preimage of the image and then prove that it will be in A0. So f of A0 means all b in the range such that b equals f of a for at least one a in A0. So then the preimage of this set is all of the a such that f of a is an element of f of A0. Okay, so we have to start by taking an arbitrary element of this set and then prove that it's in the other set. So if A1 is an element of the preimage of the image, then that means that f of A1 has to be an element of the image. So let's just call that B1 just for convenience. So then B1 is an element of f of A0. Then by the definition of f of A0, there has to be some a in A0 such that f of a equals that element. Now, we can't assume that that element is A1. That's the whole point here. For the preimage of a subset of the range, it's possible that there are elements in A that f sends into B0, even though the element is not in A0. This is what happens when the function doubles back on itself. But the definition of f of A0 tells us that there does exist some element of the subset A0 that f sends to B1. So let's call that A2. Now, in this case, though, the important thing is that f is injective. And that means that if f of A1 equals f of A2, then A1 equals A2. And that's what we just showed, because we have that f of A1 equals B1, and we have that f of A2 equals B1. So f of A1 equals f of A2, that means that A1 equals A2. We just said that A2 is an element of A0. So if they're equal, then A1 must be an element of A0 as well. And that's what we needed to prove, because we wanted to start with an element of the right side and prove that it must then be an element of the left side. Okay, so we've shown inclusion in both directions. So that means that when f is injective, A0 equals the preimage of the image of A0. Good. So the second statement that we want to show is that the image of the preimage of B0 is a subset of B0. And then that if f is surjective, then this is an equality. But if it's not surjective, then B0 might be bigger than taking the image of the preimage. Okay, so now we're going to do the same thing. Start with an arbitrary element here and prove that it's in B0. So let me just write down our two definitions again real quick. So these are the same two rules, but here a sub 0 equals the preimage of B. So the image of the preimage of B0, this is f of A0, equals all b such that b equals f of a for at least one a in the preimage of B0. And then the preimage of B0 equals all a such that f of a is in B0. First of all, remember that it's possible for the preimage of a subset of the range to be empty. If that's true, there's nothing to prove because the empty set is a subset of every set. But if the preimage is not empty, then we can take an arbitrary element of the left side and we will prove it's in the right side. So let B0 be an element of the image of the preimage of B0. That means that there exists an element A0 in the preimage of the subset B0 such that f of A0 equals B0. So if A0 is an element of the preimage of B0, that means that f of A0 is an element of B0. And f of A0 equals B0, so B0 is an element of B0. Okay? So we started with an element of this and proved that it's in that. So now we need to show that if F is surjective, then the inclusion goes the other way as well. So we start with an arbitrary element of B and show that it's in the image of the preimage of B0. So start with B0 in B0. So we need to show that it's in that. And we're going to have to use the surjectivity of F. So remember that if F is not surjective, it's entirely possible for there to be an element of B0 that is not in the image of the preimage. That's the whole point here. That all we know for sure, without knowing anything about F, all we know for sure is that this is a subset of this. But this will only be a subset of this if F is surjective. So if it's not surjective, it's possible that there's an element here that's not in this. So in the example, we had a parabola like this. Imagine that B0, if B0 is from 0 to 5, if we had an element here, 1, then there's nothing in A such that F of A is B0 here, right? So it's entirely possible for there to be an element of B0 that's not in the image of the preimage of this. But if F is surjective, that means that the whole thing's going to be covered. So then this isn't possible. It won't be possible for there to be a B0 that's in the subset of the range, but is not hit by the function. Okay, so we take an element, B0, inside the subset B0. So F being surjective means that for every B0 in the subset, there is at least one A0 such that F of A0 equals that element. So there has to be some A0 that will map to every element of B0. Okay, so that means that F of A0 is an element of B0 too. And that means that A0 is an element of the preimage. But then that means that F of A0 is an element of the image of the preimage. And this equals B0, and that's what we needed to prove, that B0 is an element of the image of the preimage of B0. Okay, so here we use the surjectivity to prove that there will in fact be an A0 such that F of A0 equals B0, and then from there it's easy. So we've shown when F is surjective, we've shown inclusion in both directions, and so that means, whoops. Okay, this is a good place to stop. There's one more little issue with image and pre-image. I'll post that discussion in a separate video, and then we'll move back to the proof of the cardinality of finite sets. Okay, here is the link to the first video in this chapter. Here is the link to the previous video. Here is the link to the next video. And click here to subscribe, and please join me on Patreon. The link to that is below in the description. Thank you.